Welcome back to G Fun Facts Online. Today we are discarding the history books and looking directly at the future of physics because we have just crossed a threshold that many scientists thought was impossible. For the last 100 years, ever since Einstein scribbled his field equations, humanity has been standing on the shore of the cosmic ocean, just watching the waves roll in. We built massive ears, like the LIGO and Virgo detectors, to listen to the splashes made by black holes colliding in the dark. We were passive observers, marveling at the faint trembling of space-time that washed over our planet. That changed this year. The physics community is currently reeling from a paradigm-shifting revelation that has been quietly brewing in theoretical circles and has now exploded into the mainstream scientific consciousness. It is no longer enough to simply detect gravitational waves. The new frontier is something called gravitational mixing. This is the active use of high-intensity light to interact with, modify, and potentially tame the ripples of spacetime itself. We are moving from the era of listening to gravity to the era of engineering it. In this episode, we are going to do a deep dive into the mechanics of this breakthrough. Specifically, how 2025 became the year we learned to touch the fabric of the universe. To understand why taming gravitational waves is such a monumental concept, we first have to appreciate the elusive nature of the beast we are dealing with. When Albert Einstein published his general theory of relativity in 1915, he described gravity not as a force, but as a curvature. Matter tells spacetime how to curve, and spacetime tells matter how to move. When massive objects accelerate, like two neutron stars death spiraling into one another, they do not just pull on each other, they churn the fabric of the universe, sending out ripples that propagate at the speed of light. These are gravitational waves. The reason it took us until 2015 to detect them directly is that spacetime is incredibly stiff. It takes a cataclysmic amount of energy to create even a microscopic ripple. The collision of black holes converts multiple suns worth of mass into pure gravitational energy in a fraction of a second. Yet by the time that wave reaches Earth, it distorts our planet by less than the width of a proton. For decades, the idea of interacting with such a wave, let alone modifying it, was considered science fiction. Gravitational waves were thought to be ghosts, passing through stars, planets, and detectors with almost zero interaction. They do not scatter like light, and they do not absorb like sound. They simply pass. Or at least, that is what we thought. The turning point came in late 2024 and throughout 2025, driven by two parallel but converging lines of research that have fundamentally altered our understanding of the relationship between the photon and the graviton. The first major domino fell with the work of Professor Ralph SCH%C3% BCTZ Hold at the HZDR in Germany. For years, quantum field theorists have speculated about the interaction between electromagnetic fields, which is light, and gravitational fields. We knew gravity bends light, known as gravitational lensing, but this was always seen as a one-way street in classical physics. Gravity acts, and light reacts. SCH%C3% BCTZ Hold and his team proposed and theoretically demonstrated that the street actually runs both ways, and more importantly, that the traffic can be controlled. The core concept here is called stimulated graviton emission and absorption. Think about how an atom works. An atom can absorb a photon and jump to a higher energy state, or emit a photon and drop down. SCH%C3% BCTZ Hold proposed that a high-intensity light wave can exchange energy with a passing gravitational wave in a very similar fashion. In this process, which coined the term gravitational mixing, a laser beam does not just get bent, it actively trades packets of energy, or quanta, with the gravitational wave. There are two main effects here. The first is the dampening effect. A laser can impart energy to the gravitational wave, slightly increasing the wave's amplitude, while the light loses energy in redshifts. But the second effect is the taming effect, and this is the most exciting part. The process can be reversed. A laser can be tuned to absorb energy from a gravitational wave. The light gains energy and blue shifts, while the ripple in spacetime actually loses power. For the first time, we have a theoretical framework where a human-made device, specifically a laser, can reduce the intensity of a ripple in spacetime. While the team in Germany focused on energy exchange, researchers at Florida Atlantic University and collaborators in South Korea uncovered a geometric secret that serves as the second pillar of this breakthrough. They discovered that when polarized light travels through curved spacetime, it exhibits something called non-reciprocity. Normally, light behaves the same way going forward as it does coming backward. If you look in a mirror, the light path is reversible. But in the presence of the twisting gravity of a rotating black hole or a passing wave, this symmetry breaks. The twist of the light's polarization becomes locked in a way that does not undo itself upon return. This finding was the key to the lock. It suggested that we can create optical systems, specifically loops of laser light, that act as diodes for gravity, allowing us to trap or amplify gravitational interactions that would otherwise be imperceptibly weak. Now, let us get into the weeds of how this machine actually works. Gravitational mixing is the term adopted to describe the nonlinear coupling of the electromagnetic tensor, which represents light, and the Riemann curvature tensor, which represents gravity. In classical physics, we treat these equations as linear approximations because the effects are usually so small. We assume light plus gravity equals light moving in a curved line. But in the regime of gravitational mixing, we look at the non-linear terms. Imagine mixing two colors of paint. Blue and yellow make green. In linear physics, the blue and yellow would stay separate dots. In non-linear mixing, they become a new entity entirely. To achieve this mixing, you cannot simply shine a flashlight at a black hole. The interaction requires the electromagnetic field to be incredibly intense and perfectly synchronized, or coherent, with the frequency of the gravitational wave. The proposed device is called a gravitational mixer. It resembles a massive interferometer, like LIGO, but with a twist. Instead of just measuring the length change of the arms, the device circulates a high-power laser pulse back and forth millions of times, trapping it between mirrors to build up intensity. The process works in 5 steps. First is inversion, where the laser system is pumped to a specific high-energy state. Second is incidence, where a gravitational wave enters the mixing chamber, or the optical path. Third is resonance. The frequency of the laser light is modulated so that the difference between the laser frequency and the scattered light frequency matches the frequency of the gravitational wave exactly. Fourth is the exchange. This resonance forces a quantum exchange where the gravitational wave is forced to give up a graviton to the photon field. Finally, the result. The gravitational wave exits the chamber slightly weaker, having been tamed, and the laser beam exits with a distinct sideband of higher frequency light. This sideband is the smoking gun. It is the visible evidence that the light has essentially eaten a piece of the gravitational wave. So why do we want to tame spacetime? The implications of this technology extend far beyond simple bragging rights. The most immediate application of gravitational mixing is in detection. Current detectors are plagued by quantum noise and thermal vibration. By using mixing techniques, we can create a squeezed state of light that is hypersensitive to gravity while ignoring other noise. But more radically, we could theoretically build active dampening systems for precision experiments. Imagine a laboratory in space that needs to be perfectly still, isolated from the hum of the universe. Gravitational mixing lasers could act as active stabilizers, absorbing the background gravitational noise to create a zone of flat spacetime for sensitive quantum computing or antimatter storage. It is essentially noise-canceling headphones for the fabric of reality. The second major application is gravitational communication, or gravcoms. If we can modulate a gravitational wave by adding energy to it or taking it away, we can encode information into it. Consider the problem with radio waves. They are blocked by planets, absorbed by water, and scattered by plasma. Now consider the gravity solution. A signal sent via gravitational mixing would pass straight through the Earth, straight through the Sun, and could reach the other side of the galaxy without losing coherence. By mixing a data stream into a passing gravitational wave, or generating a high-frequency microwave of our own using a device theoretically called a gasser or gravity laser, we could create a communication network that is impossible to block or jam. This brings us to the philosophical shift that this technology represents. The concept of gravitational mixing forces a profound reckoning with how we view the universe. For all of human history, space and time were the stage upon which we acted. We moved through space, and we waited for time. General relativity told us the stage was flexible, but it was still the stage. It was massive, indifferent, and moved only by gods like black holes and titans like stars. Gravitational mixing implies that the stage is not just flexible, it is responsive. It suggests that the fabric of reality is a material that can be woven by electromagnetic looms. If we can exchange energy between light and gravity, we are blurring the line between the container of the universe, which is spacetime, and the contents of the universe, which is matter and energy. We are realizing they are arguably the same fluid in different states of freezing. As we look at the road ahead, we must realize we are currently in the transistor era of this technology. Just as the first transistor was a clunky, inefficient piece of germanium that merely hinted at the computer age, the current proposals for gravitational mixing involve kilometer-scale lasers to affect subatomic changes in space-time waves. However, the path forward is clear. In the next 5 years, we will likely see the first laboratory demonstration of light-gravity non-reciprocity, proving that light can be twisted by local gravity in a controlled setting. In the next 10 years, the first active gravitational wave detector may come online, using mixing to amplify weak signals from the dawn of the universe. And in the next 50 years, we may see the first gravity modulators, devices capable of sending pulses of information through the bulk of the Earth using the mixing principle. In conclusion, gravitational mixing is more than just a buzzword, it is the breaking of a seal. We have unlocked the door to the control room of general relativity. By using light, our oldest and most mastered tool, to tame the ripples of spacetime, We are stepping out of the cradle of passive observation. We are no longer just watching the cosmic ocean breathe. We are finally learning to swim. Thanks for listening to G Fun Facts Online, and we will see you in the next deep dive.